Welcome to the Rendered Ingredient Lecture, a pre-course module for VM 101, Grain and Feed Mill Operations course. This e-learning web course was created by Dr. Cassie Jones, an assistant professor of feed technology in the Department of Grain Science and Industry at Kansas State University in Manhattan, Kansas. This course was made possible by FDA Grant 1U54 FD 004333-01. By the end of this lecture, participants will be able to identify rendered ingredients, list the component steps of the rendered process prior to receipt at a feed mill, identify specialized equipment used to process rendered ingredients, and list hazards associated with rendered ingredients. The rendering industry is vital to the sustainability of the animal feed industry because it allows us to utilize products that would be otherwise unused as feedstuffs. It amounts to a total of 48 billion pounds of rendered products annually, 5% of which is from restaurant grease, 4% from grocery or butcher waste, and 91% from slaughter byproducts. A very small amount, less than 1%, is from dead or downer carcass disposal. The percentage of live weight of carcasses that would otherwise go unused includes 49% of the live weight of a beef cattle carcass, 44% of pork, 37% of broiler chickens, and 57% of fish. Importantly, the chemical composition of rendered ingredients are generally very desirable as animal feedstuffs. On average, raw ingredients are approximately 40 to 60% water, 20 to 30% protein, and 20 to 30% fat. 31% of the protein bone products are accounted for as ruminant meat and bone meal, while another 15% is mixed meat and bone meal from both ruminant and non-ruminant animals. Both of these products are prohibited from use in ruminant feed. However, the remaining 56% of rendered protein meals can be fed to ruminants, and these include poultry byproduct meal, non-ruminant mammalian meat and bone meal, feather meal, ruminant blood meal, non-ruminant mammalian blood meal, and other proteins. Some of the most common animal proteins used to manufacture animal feeds include meat and bone meals, poultry byproduct meal, spray-dried animal plasma, fish meal, and blood meal. Meanwhile, all fat products that contain not more than 0.15% insoluble impurities are technically allowed to be fed to ruminant animals. Over 55% of all rendered fats are in the form of edible or inedible tallow, which is derived from beef fat. Edible tallow is used in products like margarine, cooking oil, or baking products. Inedible tallow is used to produce products such as soaps, candles, and lubricants. Nearly 20% is yellow grease, or used cooking oil from the fast food industry. Meanwhile, 11% is choice white grease derived from pork fat, but not refined to the level of edible lard, and 10% is poultry fat. Here are some pictures of common rendered ingredients used in animal feed. The top row are products derived from poultry, such as feather meal, poultry meal, and unbleached poultry fat. Feather meal and poultry meal are similar in color. The second row has products derived from either beef or pork, such as meat and bone meal, blood meal, and spray-dried animal plasma. Meat and bone meal is usually light brown to light pink in color, while blood meal is very dark red, and animal plasma is white and very powdery. Fish meal, pictured in the bottom left corner, is medium brown to green in color and has a very distinctive fish smell. Finally, there are a variety of fats from the rendering industry. Beef tallow is the most saturated of the fats and looks similar to soap. Choice white grease is slightly less saturated and has a consistency and color similar to lard. Finally, yellow grease can vary widely in consistency, from fairly liquid to more dense. The protein content of meat and bone meal is widely variable. This is due to the wide variation in raw materials that can be used as rendered products. For example, the protein content of ruminant meat and bone meal during the time period shown was 53.6%. However, there was a wide standard deviation, 6% points, and individual samples varied from 45 to nearly 60% protein. Variation in composition leads to a wide variation in amounts included per ton of feed. It is a difficult ingredient to use. The quality of fat products is important because they can easily go rancid. Thus, the MIU, or percentage moisture, impurities, unsaponifiables, is often calculated and assayed. Other considerations include free fatty acids, peroxide, anisodine, and iodine values, fat color, and the active oxygen method for 20-hour stability. Of these tests, those to measure rancidity or oxidation are most important for hazard prevention. The rendering process involves taking raw materials, sizing them, applying heat, pressing to differentiate the proteins from lipids, grinding, and storage or loadout. Of these processes, the most important for potential hazard control is the heat processing step, which destroys pathogens and removes water to prevent future pathogen growth. Wet rendering exposes raw materials to water heated to 180 to 205 degrees Fahrenheit, and the water is later evaporated. This process is not very energy efficient and results in poor fat quality, so it is no longer used in the United States rendering industry. In the modern U.S. rendering industry, the cooking process occurs through a dry rendering process where raw material is dehydrated in either batch or continuous cookers, maintained at 240 to 290 degrees Fahrenheit for 2 to 3 hours. Temperature, time, and pressure is all important to pathogen destruction, so raw product must be maintained at 250 degrees Fahrenheit and 2.8 bar pressure for 45 minutes, or 275 degrees Fahrenheit and 2 bar pressure for 30 minutes. After the dry rendering process, any remaining water is drained. The solids are pressed in either a single or double screw press to extract some of the fat from the protein components. Regardless of the method used, it is important to understand that the temperature and time of the cooking process, as well as subsequent steps to prevent recontamination, are vital to producing pathogen-free rendered products. During the receiving process, products are sorted by size, by sifters and grinders. It is important to facilitate proper cooking of various sized ingredients. The heat processing step is undoubtedly the most important aspect of the rendering process. There are 3 main goals of this process. First, destroy pathogens that may have been naturally present in the raw material. Second, melt fat to facilitate its separation from the bone and protein, similar to how fat melts in a pot roast, allowing the bone to be easily removed. And third, remove water. As described earlier, this step is the most important to prevent potential hazards. Undercooking can result in improper water removal and/or incomplete pathogen destruction. For this reason, both quality and safety controls are necessary at the completion of this step. After heating, a screw press separates the fat from protein and bone in an enclosed vessel. This fat can then be refined to remove moisture and impurities. The protein and bone can be kept together, dried and ground, or further refined to a variety of protein and mineral products. Food safety hazards are broken into 3 categories: physical, chemical, and microbial hazards. Physical hazards include those materials that may be found in either the rendering plant or where the ingredient was sourced. such as a slaughter facility. Thus, these physical hazards may include glass, metal, or wood. While many sources of chemical contaminations are possible, cleaning materials used in facilities have the greatest potential as a chemical hazard. Certainly, one must be concerned about potential biological hazards in rendering products. Raw materials have been demonstrated to contain relatively high concentrations of E. coli, salmonella, and other pathogens. That said, the rendering industry has a rendering code of practice that is preventative in nature. This practice is based on HACCP-like principles that follow written procedures and process controls for feed safety. This process is verified by third-party auditors. There are 117 certified plants in the U.S. This practice demonstrates that the rendering industry approaches hazard analysis from a preventative rather than responsive perspective. The United Kingdom Department of Health released data in 2001 summarizing the potential health risks for humans associated with various methods of animal carcass disposal. In its summary, they found that the rendering process resulted in the least exposure of humans to pathogen hazards, particularly compared to landfill or burial. The agent causing bovine spongiform encephalopathy was the only exception, where rendering was considered a moderate risk compared to incineration, which resulted in a negligible risk. Since the time of this study, the U.S. rendering industry has imposed higher cooking standards and additional critical control points. They are now considered negligible risks to humans after rendering. Additionally, the ruminant feed ban has further lowered this as a potential hazard, as restricted ruminant proteins cannot be fed to ruminant animals. Certainly, incineration of animal byproducts and/or carcasses will always pose a lower risk, but there is no subsequent value of the incinerated product. This data from Truitt and others in 2001 demonstrates the success of the rendering code of practice and the importance of heat processing. A variety of raw tissue and post-process samples were collected from 17 different rendering facilities. The raw tissue samples had a very high rate of contamination for Clostridium, Listeria, Campylobacter, and Salmonella, but there were no positive samples after processing. This is a good demonstration of the efficiency of the rendering system to destroy pathogenic bacteria. These results also point out how important it is for a facility to adopt practices that reduce or eliminate the opportunities for post-process contamination of their finished products. In summary, we have identified common rendering ingredients as feather meal, poultry meal, meat and bone meal, blood meal, sprayed dried animal plasma, fish meal, poultry fat, beef tallow, choice white grease, and yellow grease. Rendering includes multiple steps, including receiving and sizing, cooking, and pressing prior to grinding. Of these steps, the cooking process is most pivotal. Specific equipment used in rendering includes the sizing equipment and knives, cookers, press, and hammer mills. The potential feed safety hazards include physical or cleaning chemicals found inside slaughter or rendering facilities, and potential microbial risks. However, the rendering code of practice minimizes these risks in a preventative manner so that rendering ingredients actually pose a low animal feed or human food safety risk. This course was made possible by funding in part by the Food and Drug Administration through a grant to Iowa State University and Kansas State University. Thank you.